Hey everyone, so we just finished talking about horizontal projectiles. In fact, we also talked about vertical projectiles as well. What we're going to do now is kind of combine the two topics together and talk about angular projectile motion. So this is pretty much can be considered the more general case. Technically, horizontal projectiles is a form of angular projectiles where we're starting at the very maximum height of it and then seeing the resulting case. And vertical projectiles is essentially angular projectiles, but straight up. Um, so we're pretty much going to do a little bit of both aspects. There's a lot of stuff from the vertical projectiles that carry over, and a lot of stuff from the horizontal projectiles that gets carried over too. The one thing that we do have to pay attention though is we're going to have to bring it back the idea of vectors. Now, once again, since we're doing two-dimensional motion just like with the horizontal projectile, we're going to have to make an XY chart, again, to organize our information. Uh, the motion that's going on, the information that's going on in the X direction is independent of the stuff going on in the Y, so we have to make sure that we're separating the information uh, so that we know which numbers go into equations together. If we start mixing and matching between X and Y, we're going to end up having a bad time. Now, just like last time with the horizontal case, a lot of numbers are going to stay the same. For example, the initial X position is going to stay the same since most of the time the projectile is only going to be going forward. Therefore, we can pretty much say that wherever it starts, that's the initial X position. The acceleration in the X is also still zero. There's no horizontal acceleration. And the vertical acceleration is once again negative 10 meters per second squared. Now, as far as the Y direction, there's not really a whole lot other stuff that we know. We don't know the initial velocities this time. We don't know where it's starting. Some problems may have it start at the bottom, where so Y might be zero. Sometimes it might start at the top, so it's going to start with some initial Y value. It could end up going to the ground, so that final position might be zero. Maybe it starts and ends at the ground. We don't really know, so we need a little bit more information before we can start plugging stuff in for the Y. But for now, this is the stuff that we'll know for pretty much every angular projectile problem. Now, the next step is something where that is different from the other problems that we really have to make sure we do. So, one thing that makes angular projectiles unique is that we're going to end up having the velocity at an angle, hence the name angular projectile. Now, if you recall last time when we did the vertical projectiles, they gave us a velocity. That velocity was our initial vertical. When we did the horizontal, the velocity that they gave us was our initial horizontal. And the initial vertical was actually end up being zero. Now, when they tell us a velocity at some angle, what they're telling us is that some of our velocity is going to be in the horizontal direction and some of it will be in the vertical direction. So what we have to do is we have to use the stuff about vectors and components in order to figure out, well, how much of the velocity is horizontal and how much is vertical. So when they tell us that the initial velocity is, let's say, 30 meters per second at 30 degrees above the horizontal, what I need to do is not put the 30 into my chart, but instead realize that my x initial velocity is 30 cosine 30, and my initial y velocity is 30 sine 30. So this is the amount of velocity that's pointed upwards, and this is the amount of velocity pointed horizontally. Now that we have this velocity, we can actually, just like with the horizontal projectile, because the acceleration is zero in the x, we can just say that these two velocities are the same. From there, the other information that we plug in, it really kind of depends on stuff that they tell us. Um, One thing that I usually kind of say is that when you make the chart, sometimes it helps to just treat the y direction just like you would with any standard vertical projectile. Now, what I mean by that is, if you recall, there was key information that they would say that gave us extra pieces of information. So, for example, if you're reading a problem and it says that it starts at the ground and then lands at the same height or same surface, that's telling us that the initial and final positions are both zero. If they tell us that the object goes to its maximum height, then that tells us that the final velocity in the y is zero. So we can kind of do the same thing. Look out for these same exact context clues, key phrases, just like we did with the vertical projectiles, and use that to find information to plug in for the y. The x direction honestly doesn't really get used. Just like with the horizontal projectile, it is extremely finicky. So the only time you can ever do anything with the x is if you're really only missing one piece. So since x naught and a are always given and the final velocity doesn't really matter, that means the three pieces that we have to worry about are the final position, the initial velocity, and time. If we're missing more than one of those, so if we're missing two pieces of those three, then we cannot solve this problem. So most of the time, you're going to be focusing on the y side and then using any information in the y through time to find the x values. Commonly, the x is really going to be used to find the range, but sometimes it may end up being used to find the initial velocity or anything like that. Basically, the idea, though, is that you're most likely going to have to do something with the y before you can do anything with the x. Again, kind of going back to what I said before, if it starts at the same, if it has the, lands at the same surface, then that's kind of telling us that the final position in the y is zero, as well as the initial position. And we can also make the other claim that we did with the vertical projectiles, which was that the time and the velocities are symmetric. That whatever the velocity is going upwards at that point, initially, that's going to be the same velocity going downwards. But again, that's only true in the symmetric case. It's going to be very common that instead of dealing with a symmetric projectile, that you might actually deal with an asymmetric projectile. Honestly, nothing really changes. The only difference is that, well, we won't have the final position in the y being 0. It'll be some other number, or the initial position in the y is going to be some number. It honestly doesn't really change much, but for the most part, it ends up being tackled the same way. The only thing that you're going to have to be careful about is that there's a good chance that you might end up with a quadratic equation when you try to use the annoying x. You can get away with this or go around this by using the timeless equation, the v squared equals v naught squared plus 2a x minus x naught, along with the acceleration equation, v equals v naught plus at. But the one thing that you really have to pay attention about is when you use that v squared equation, because of the nature of the solving for velocity, when you do the square root, you have to remember that you either do plus or minus of that number. If they tell you whether the ball is on its way up or on its way down, you can easily figure out what the signs are. But if you don't actually know which one it is, then you won't be able to solve it properly. So you're going to have to be a little bit careful with that. All right. So the general setup for angular projectiles, besides the whole like making the chart, the very first thing that I actually recommend that you do before you even think about making the chart is split that initial velocity into its x and y components. This is important not just for this topic, but pretty much anything that we talk about where we deal with vectors and things at angles. That's going to be a very common first step. So get into that habit now, and it'll help you later on. But you're going to take that velocity, find its x and y components, and then what you're going to do is make an xy chart with those numbers. Then, as I mentioned before, the vertical direction is basically the y direction is just a vertical projectile, and the x direction is just constant velocity. So nothing too crazy. So this is going to be the first question, just like with the horizontal projectile. I want you to draw the three motion graphs for the x direction. So pause the video, work stuff. We'll go in a second. Just like last time, what we want to do is work our way backwards. Acceleration is the first and easiest one because it's either constant, positive, or negative. There's no other, choices. So if I look at my chart, think about what the acceleration in the x direction is. I know that the acceleration is 0. Since my acceleration is 0, I know that my velocity doesn't change. Again, I know this from my chart that whatever my initial velocity is, my final velocity is. So since it's going to start with the positive velocity, I know it's going to be a constant positive value. Again, this makes sense because the slope of velocity is my acceleration, and the slope of this graph is 0, and my acceleration is 0. For my x position, I know that it's going to start at 0, so my graph is going to start at the origin. Since the velocity is constant and positive, that means the slope of this graph should be constant and positive, meaning that I'm going to have a linear line. So these are the three motion graphs for the x direction of an angular projectile that's shot and lands on the ground. All right, here's the next one. So now we're going to do the y direction. So pause the video, works up. We'll go over in a second. All right, so here we're going to do the same thing. We're going to start with the acceleration. This time, since we're looking at the y direction, we know that the acceleration is negative 10. So it's going to be a constant negative 10. Again, no lines, no curves, just a constant straight line. Now when I go back to velocity, I have to use, all my knowledge for this one. I know that the velocity is going to start in the positive direction because it's being shot upwards. If the velocity wasn't initially positive, it wouldn't go up. So my velocity is going to be initially positive, and since my acceleration is negative and constant, I know my graph should become negative and be a linear line, constant slope. I also know that it's going to follow this path because I know that when I shoot the object up vertically, it slows down, just like this graph is doing, reaches a maximum height, and then starts speeding up in the negative direction. So that's exactly what this graph is showing. Going back to x, so since it's shot and lands at the ground, I know it's going to start at 0 and end at 0. And then what I can do is use this graph to figure out how it's drawn. Because this graph is linear, I know this should be curved. I could probably guess that it's going to be parabolic, but just to make sure that it makes sense, this velocity starts off positive, goes to 0, then goes negative. The slope of my position graph, which is velocity, my slope should do the same thing. So in the beginning, my slope is positive, the graph goes up. Then in the middle, the slope goes to 0. It flattens out and hits a peak. And then at the very end, the slope goes negative. It goes down. So yeah, these three graphs would represent the angular projectile. Now, if you look back when we did this for the horizontal projectile, you'll notice that the graph started here and then went down. And then this one started here and then went down. So as I said before, the horizontal projectile really is just half of the angular projectile that we've done. All right, so here's the first question. So pause the video, work itself. We'll go in a second. All right, so as I mentioned before, the very first thing that we want to do is break up the velocity. We have 24.5 meters per second at 35 degrees. So we're going to do 24.5 cosine 35 and 24.5 sine 35. We're going to make our chart, and it's going to look like this. So again, because of the components, I can plug those numbers into here. I know that it lands at the same height, so my final position is going to be 0. So to answer part A, where it says what's the total time in the air, because the x value is missing the final position, I know that the y value is going to be what I'm going to focus on. So I'm going to use the annoying x equation in the y direction, plug my numbers in, and I get 2.8 seconds. Now, to find the position, the x, what I'm going to do is I'm going to take this 2.8, since the once it stops moving vertically, it also, you know, has to stop moving horizontally. We're going to put in the 2.8 on the x side as well, and once again use the annoying x equation, but for the x side. Plugging those numbers in, we end up getting that it reaches a range of 56.3 meters. And then part C asks for the ball's max height. Now, I could do this a few different ways. Since this is going to be a symmetric case, I can actually half this time and then just do the annoying x equation a second time, this time looking for the final position. I could do that, but one of the things I would recommend is try to avoid taking advantage of symmetric cases all the time. I know it sounds a little counterintuitive, but the reason why I recommend it is because you want to make sure that you're doing something that will always get you the answer. And if you are constantly practicing the case where it's symmetric, then you'll forget to pay attention when it's asymmetric. You might accidentally do it in that case, or you won't know how to figure it out in that case because you can't just half the time. So my recommendation is get into the habit of using the v squared equation, the timeless equation, because this is something that's always true for max height. Because we know what the final velocity is, it's going to be zero. We know what the initial velocity is, it's whatever they tell us. The acceleration is negative 10. So plug the numbers in, and I get that the max height in the y direction is 9.8 meters. All right. So here's the next question. Pause the video, works out. I'm going in a second. So 11 is pretty much the exact same question, just with slightly different numbers. So my chart ends up being pretty much the same. Again, I take the velocity, the 18 meters per second at 55 degrees, find the x and y components, so 18 cosine 55 and 18 sine 55. And once again, the final position, the y is going to be 0 because it lands at the same height. We're, again, doing the exact same calculations. So we're going to once again use the annoying x equation to find the time of flight, focus only on the y side, plug these numbers in, get 2.94 seconds. Once I have this time, that's going to be true for both x and y side. So use the annoying x a second time, this time looking at the other column. Plug the number in, and we get 30.3 meters. For part C, we'll do the same thing using the y side. Use the v squared timeless equation, and then plug our numbers in, and we get 10.8 meters. It's important to remember is that this chart is really only being used right now for A and B. If I wanted to use the chart for part C, I'd have to change my numbers. I would not be. I would have to get rid of the final position in the y and replace the final velocity in the y with 0. All right. Here's question 12. Pause the video, work itself. We'll go in a second. All right. Now, when we go to plug the numbers in, the one thing that we have to actually be careful about is that not every number given is going to be used. One of these numbers in particular is what we will call a reference number. And that number is the 4-meter gap. They tell us that the two buildings are 4 meters apart, with the second building being 1 meter below. And then later on, it asks us basically how far does he jump? Does he make it across the second building? Because of the fact that we don't know if he makes the 4 meters, maybe he jumps a little bit less, maybe he jumps a little bit more. We don't know if the end of the problem when he lands, he's going to be 4 meters across. I can't put the 4 into my chart. The 4 is going to be what I use to compare my final number to. The only number that I actually do know that's going to be true is the 1 meter, because it's telling me that the second building is 1 meter below him. And we know that if he's landing, ideally, he's going to be landing on top of the building. So he will land vertically 1 meter below where he is, or at least that's what we're going to be focusing on. So when I make my chart, I again do the same thing. I do the whole 7 cosine 30, 7 sine 30 to find the initial velocities. The standard numbers go in, The one thing I do though is I set the initial position in the y to be 1, or the final position in the y to be 0. So I'm starting it at some initial height and having them go down. If you wanted to, you could always make the initial position 0. You just have to make sure that the final position is -1. Doesn't really matter, but sometimes it's helpful to try to minimize the amount of signs you use. So from here, what we're going to do, again, we're trying to find this position in the x. We don't have the time, so we're going to use the y side to find the time. Plug the numbers in and get that he's in the air for 0.92 seconds. Once I have that, that's going to be true in the x side, so I can use the equation a second time. Plug my numbers in, and I end up getting that he lands 5.58 meters. So going back to the original question, can he make it across the building? Yes, he actually makes it by an additional 1.6 meters past where the second building is. All right. Here's the next one. This one actually has a third part, but we're only going to focus on part A and B. So pause the video, work itself. I'm going to go for a second. All right. Once again, just like in the previous case, one of these numbers is not going to be plugged into the chart because it's going to be used as a reference number. Again, it's because this is the number that isn't describing what the ball actually is doing. And that's going to be the 3-meter goalpost. Again, the football may not reach 3 meters. It may go above it. It may end below it. The only thing that I do know is that it will reach horizontally a distance of 30 meters. So my chart will look like this. Ignore this because that was a mistake, actually. So we'll just cross that out because we are actually looking for the final position in the y. But besides that, again, going with the whole 18 sine and 18 cosine 40 for the initial velocities. What we can do is use the x side this time, because now if we try to use the y side, we don't have nearly enough information. But if we look at the x, we have everything else. The only thing we don't have is time. So what we can do is use the x velocity or x values with the annoying x to find how long it was in the air for, 2.17 seconds. And now use that 2.17 seconds with the y values in the same equation, plugging it in to figure out where the ball is vertically. So by the time it reaches the goalpost, it's going to end up being at a height of 1.63 meters, which means that it will not go over the post. It will actually be below the post by about 1.37 meters. A follow-up to this is what is the max height of the football. So again, the chart isn't really super helpful for it. What we're going to say is that this number is 0. And again, we're going to use the v squared timeless equation. Plug my numbers in. And I get that the max height is 6.73 meters. So it turns out that the football will vertically go higher than the goalpost, but because of it reaching that height before it reaches the the 30 meters where the goalposts are, by the time it does get there, it'll end up being below where the posts are. So yeah, that's an important thing, that just because the football does reach a height of 3 meters doesn't mean it will reach a height of 3 meters by the time it reaches the posts. All right, and then here's the next question. So pause the video, work itself. We'll go over in a second. All right, so now we want to know is how we can find the velocity needed for the football to just make it over the goalpost. Now, this actually is a very unique phrasing that you may not know right off the bat. But typically, when they say that it just makes it over there, that means that in this case, this is one case, that the maximum height that it reaches is 3. So it's just making it over. What this means is when we do our values, this time we will say that the final position y is going to be 0. But one of the other things is that we're going to say is that the final velocity is going to end up being 0 by the time it reaches there. And this is what I'm going to end up working with. Now, one thing that we have to be careful about, we can't actually do the v squared timeless equation. It may seem like we can, but it's not going to work out properly. Mainly because of the fact that there are other scenarios at play that will allow me to reach a max height of 3 meters with a different velocity. So I actually do want to include both the x and y direction. And I also want to do it this way mainly because I want you to see what would happen if you have no way of getting it using a single equation. So what I can do is look at the x side, since we have so many of the variables, and start solving. And then I'm going to get to a point where I realize that I have two unknown variables. So I don't know the initial velocity v and I don't know the time. So one thing I'll do is I'll just rewrite this so that it solves for, let's say, time. My end goal is to figure out what the final velocity, the initial velocity is. So let's solve it like this. We'll write it as time equals some number divided by v. I'm just solving this. I'm moving the v cosine 40 over to the other side, figuring out what that is, and leaving it in that v term. Because this is as far as I can go here, I'll stop and I'll think, okay, well, since I have two variables in this equation, that means I need a second unique equation. So instead of just looking at the x side again, I'm now going to switch my gears over to the y side, use the exact same equation. Actually, not the same equation, sorry. I'm going to use the acceleration equation. Again, use the numbers on the y side. I get the same two variables that I don't know. I don't know v and I don't know t. So now I can take this and rework time in terms of v. With this, I now have two different equations that solve for time in terms of speed. What I can do, since these two equations are representing the same motion, I can set the times equal to each other because it's the same, right? We've said this many times that the numbers that we use on the x side and the numbers we use on the y should give us the same time. So I can set the 39.2 divided by v equal to the 0.064 v. From here, I cross multiply. It may not be easy to see because of the way it's written, but I'll end up multiplying the v over to this side to get a v squared, dividing the 0.064 over to the other side to get v squared equals 612.5. Then take the square root and get 24.75 meters per second. And that's pretty much how we figure out the velocity to just make it over the goalpost. There's one other thing that we want to talk about. We kind of talked a little bit about with the horizontal projectiles, but we want to talk about it in the angular projectiles. We should once again know some of the factors that would affect the range, max height, and time in the air for the projectile. We're not going to kind of rehash a lot of this stuff because the things that affected it in the horizontal case is going to affect it here. So one thing that we talked about is how increasing the initial horizontal velocity didn't affect time in the air, and the same thing applies here. Increasing the horizontal velocity will not affect the time in the air for the projectile. Though now, because the projectile velocity is affecting both x and y, making the statement of changing the initial velocity will actually affect time in the air. So it's only in the case where we just make sure that whatever we're changing, we're not changing the horizontal component. That would be the only time where the time won't change. But changing the initial position, changing the gravity that it's being experienced, the air friction, all these things will affect the time in the air and the range. And it's going to affect it in a very similar way. So we're not going to rehash that. Instead, we're going to focus a little bit more on the angle, the thing that's different about this from horizontal projectiles. So we need to know, how does angle affect range and time in the air? So I actually have this little simulator from the FET website where I can take my projectile and I can just shoot it at different angles and see what's going on. Now, I would definitely recommend that you try this out yourself. You go to the website fet.colorado.edu, type in the search bar for projectile motion, and choose. It works on pretty much any browser, but choose the intro section and try to think about how you would set up this an experiment to figure out what angle or angles would give you the greatest max height, greatest range, and give same ranges. The one thing you'd have to make sure is that you kind of dip it a little bit. Unfortunately, it makes it so that Canon can't shoot lower than 25, but that's good enough for us. All right, so you can think about it. You could pause this, and I'll end up going on and start explaining what you would do. All right, so what I would do is I would start at 25 and then go up by 5 degrees all the way up to 90, making measurements of time, range, and height for each of the points, and then just see what happens. Now, I'm going to do actually, I'll do four angles in particular. So 30, 45, 60, and 90. Now, if you notice, there's a bunch of these dots here. I can take this and hover it over, and it'll give me the information at that point. The one problem is that it can get a little bit hard to read the final location points. So what I'm going to do instead is I'm going to locate the middle point, this green point on all these. That represents the maximum height. So if I look here, this has a maximum height. It reaches in a time of 0.76. This one goes up to reaches its max height at 1.08. This reaches at 1.32, and this reaches the max time in 1.53. So what we can see is increasing the angle increased the time it was in the air, because the time it took for it to reach max height kept going up each time. So it turns out 90, the highest angle that we get to, will give us the greatest time in the air. I know it didn't say it here, but it's still useful to know. The next one, the height. So I look at here, 2.87, 5.73, 8.6, 11.47. So just like with the time, the height also increases as I increase the angle. So once again, 90 degrees will end up giving my maximum height. If I go to 15 to find the angle that gives the greatest range, well, I'm going to look at the range number, 9.93, 11.47, 9.93, and 0. So it turns out that 45 will give me my greatest range. Since we kind of skipped a bunch of angles, in a good experiment, what you would do is kind of go above and below just to make sure that this wasn't, happen to be a max for this setup. But I will tell you now that 45 is actually the angle that gives the greatest range. And then the last part, which angle gives the same range? Well, we already can see it here that 30 and 60 give the same range, 9.93 and 9.93. But it's also important to note that those aren't the only angles that will let me do it. If I instead go to 65 and 25, these two will also reach the same range of 8.78. If I go to 35 and 55, these two also reach a range of 10.78, and 50 and 40 will also reach the same range. So it turns out that any angle, any two angles that add up to 90 will give the exact same range. So it turns out to be complementary angles. So the answer to these questions would be 90 degrees, 45 degrees, and complementary angles. Um, there is one last thing that I do want to point out since I'm using this. All this stuff that we're talking about, or at least for number 15, the giving the greatest range, and 16, the same range. This is only true when we're shooting an object from the ground. If I instead increase the height of the projectile, it turns out that my maximum range will no longer be 45 degrees. Um, yeah, you can. It's very hard to see it here, but this one is should be the 45. It has a range. Actually, it's a little bit hard to see. Right, right there. It has a full range of 26.41 meters, but 40 degrees is a little bit further with 26.63. So it turns out that when I increase my starting height, the maximum range no longer ends up being 45 and will actually decrease the higher I go and become more noticeable the higher I go. So you can see it here that 40 went a little bit further. Uh, I don't know if 30, okay, 30 actually is really hard to see. So it might actually be an angle between 35 and 40 that would give me my maximum range this time. But I can keep doing this, for higher and higher heights and see what I end up getting. So this would be 45. I think I'm starting to get to a point where I can't really see the values too well. 35, 40, and then let's do 30. And we could already see that 30 and 35 kind of end up going a lot further than 40 and 45 did previously. So it turns out that as we increase the height is actually increasing the time in the air, allowing us to not have to shoot the projectile as high up. We can now shoot it a little bit more horizontal to give it a much longer range. It's a little bit interesting effect that's important to note. So I just figured I'd share this with you so that you know that shooting it from a higher height invalidates our discussion about the whole 45 being the greatest range. It now has decreased to something a little bit lower. All right, that's angular projectiles. I know this was a little bit longer, but if you have any questions, feel free to let me know. Otherwise, good luck and have a great day.